Hi everyone, and welcome to a quick demonstration on how to run your in Google Sheets or Excel. I posted a little while ago instructions on how to install XLMiner or the data analysis tool pack. XLMiner is what we use in Google Sheets. The data analysis tool pack is what we use in Excel. I'll just quickly those instructions. They're on our class slides from the last class that we had. So in Google, go to your add-ons and search for XLMiner. It should work. For Excel, you can also go to add-ons and search for data analysis and follow the instructions again. If you are struggling with this, please let me know before Monday's office hours. Okay, now I'll just show you where add-ons is in Google Sheets because that's what most of us use. So here's the add-ons tab at the top. This is just a sheet I'm using to do this example. I'm not going to share it. It's not available to you. I prefer that you work through your own example following this. So here's tab. Here's the XLMiner analysis tool pack on mine because I have it installed already. If you don't have it on your list, you can go to get add-ons and then search for XLMiner and you should be able to find it. I have mine installed already, so let's kick off the lesson. So let me just take that out for now. What I've done is I've created a data set that looks it's a simulation essentially, the examples that we had in our last class, where we were trying to come up with the type of data, the type of samples, and the purpose behind different hypothesis statements. One of the hypothesis statements we had was that students spend less than 3 hours on average on additional hypothesis and alternative. Remember, your alternative is the claim you're trying to make. The average amount of reading time is below 3 hours. That's the claim I'm trying to make. In my null, I'll essentially have the opposite of that sign, which is anything above or equal to 3 hours. You'll see in some of the ALUX videos that people do different things in the null hypothesis. Some people prefer to just always have an equal to sign and essentially say that equals to sign encompasses everything that is not this. So you may find this terminology, or you may find that they specifically say greater than or equal to. Either one is fine. Okay. What you do want to make sure you get right is your alternative for sure. That sign has to match whatever you are trying to prove. Okay. Now, here is a sample of data from .24 students. So I've got a little counter in the corner that tells me basic stats. So this is 24 observations. There's my count. So this is 24 students reading hours. Student 1 reads 1.5 hours after school, 2 hours after school, doesn't read at all after school, etc. And I want to execute my hypothesis statement, my hypothesis test for this data. So I'm going to start XLMiner. And it will come up on the right. And it does a lot of different things. So you'll see a long menu. The kinds of tests that you will notice we are covering tests and Z tests in your hypothesis testing self-work. I'll briefly explain now. After this example, I'll explain when to use a t-test or a z-test. Because we are looking at a data set that we don't already have a standard deviation from the population for, we're going to be using a t-test, not a z-test. So you only use the z when you know the standard deviation from the population. It is rare to know anything from the population, so chances are you will mostly be using t-tests. Okay, now here is my t-test list. There's a paired two sample for means, and we defined paired and non-paired last time. Here I've got one sample, so I don't want a paired anything. So it's either the two sample assuming equal variances or the two sample assuming unequal variances. Unfortunately, this list doesn't have a one sample test. So what we'll do is we'll choose a two sample test assuming unequal variances. I'll explain why we assume unequal variances just now. And we'll create a dummy variable for our second sample. So in order to be able to use that two sample test, we actually have to have two samples. Because I only have one sample here, I'm going to create what I'm calling a dummy variable. Let's call it second sample, so dv for dummy variable. I'm just going to put zeros. Okay, XLMiner will work without any real data in here. It just has to get some kind of range. I can give XLMiner my ranges that I want to look at. So I'm going to click on reading hours and click in there, and it will load the range. So you select your range first, and then you click where it needs to go, and it loads automatically. I'm going to do it again for variable 2, which is the dummy range. So I'm going to select my dummy range. Then I'll go click in the box for variable 2, and it should load automatically. And it has loaded B3 to B11. Okay, bear in mind this is the dummy variable. Because it's zeros, Excel will know what to do with that. Now, remember when we talked about the purpose in class, we said sometimes you're comparing two statistics, sometimes you have a hypothesized value that you're comparing against, and sometimes you are looking at a relationship. If we were comparing two statistics or we were looking at a relationship, we wouldn't have any hypothesized value to put here. Okay, so there'd be nothing to go in here. Because for this particular example, we do have a hypothesized value, we're testing against 3 hours. That's what the statement says. We want to see if they spend less than 3 hours on average. So my hypothesized value here is 3. This little checkbox is something you select if in your range for your variables, if you selected the titles, then you have to click labels. You can see here my titles are in row 3. So I've selected from row 3 to the end, which means my title is included. So I have to click the labels. Please always include the title. If you don't include the title, Excel will assign variable 1, variable 2, and it can get pretty confusing if Excel does the assigning for you. So preferably include your labels so that it keeps calling each variable by its real name. And then for my output range, I want it to just happen somewhere on the sheet, okay, just not over any of my original data. So I'm going to click any empty cell and then click in the output range, and it will load the cell I've clicked, cell E3. That's where it will give me the results for this hypothesis test. And I'm finished, so I'll click OK. And you see there's my two variables that I'm comparing. If I didn't click these labels, or if I didn't use the label function, this would say variable 1 and variable 2. And when you actually have two samples, you can get confused because these won't be zeros, they'll be numbers, and you won't know what's what. So always use your labels. Now, XLMiner gives us this nice output that tells you your mean, your variance, the number of your observations. That's how big your sample is. We knew that was 24 already. We should have actually calculated the mean and the variance in the beginning, just to follow the sequence of what we've been doing. So in week 1, you learned how to find the central measure using either the mean, the median, or the mode. We can do that quickly. I'll do it at the bottom here. I had made space for it. So I'm going to find the average of all of this data. Don't include the title here, just the range that you want to put the function on. And this is my mean. I'm also going to find the standard deviation. And remember that these are what we call our descriptive stats. Your standard deviation and your mean basically just and summarize it for you. I'm going to write here standard deviation, and I'm only interested for my sample, not for my dummy sample. Nobody cares about that. It's just a dummy sample for XLMiner. So here's my mean. You'll see it's the same as the output that I got from XLMiner, so that's good. The standard deviation and the variance are related in this way. Remember that represented by an S. Variance is just the standard deviation squared. So this is S to the power of 2, okay, S squared. So if my S was 3, my variance would be 3 to the power of 2, and my variance would be 9, okay? In this case, I have this variance. Let's copy that again. Copy. And you want to paste the value. Okay, and I want to square that number. So take that, square it to give me the variance. And you'll see my variance matches what came out of my XLMiner output. So I'm happy with that as well. Okay, whether you talk about standard deviation or variance, it doesn't really matter. They give the same kind of information. They talk about the variation of your individual data from the center, the variation of all your observations from the mean. Okay, now we said already our hypothesized mean was 3, so we're fine with everything up to here. Degrees of freedom is something we haven't spoken about, but ALUX explains it. It's typically n minus 1. There's a pretty good explanation on ALUX. I won't go into that because it's not the focus for today. So n is our sample size. 24 minus 1 gives you 23. What we are interested in is the p-value. So everything that comes, I'm just going to remove this stuff. Everything that comes here is essentially the information around our hypothesis test. Each p-value goes along with what is called a t-statistic or a t-critical value. The one that you want to interpret is the one with the p, the probability value. So the rule that you need to remember for validating your alternative hypothesis test is that if your p-value is less than alpha, then reject H naught. And if you think about what we're trying to do, we've got an H naught and an HA, and based on some measure that tells us how significant our findings are, we want to essentially say, this is true, this is not true. Okay, we want to reject this null hypothesis and say that our claim has been validated. So this is the rule. When your p-value is less than alpha, then you can reject your null. Then you are happy because your alternative is validated. A quick way to remember this, I have a little acronym. If your p-value is less than alpha, reject H naught. So PLAR is the acronym I use to remember that statement. My p-value is always 0.05. My alpha, sorry, not p-value. My alpha, which is my level of significance, is always 0.05. This is a standard that's been set in the field of statistics. It's the percentage that we want to be able to reject H naught for. Okay, it essentially coincides with, we talked about confidence intervals at the beginning of the semester. Alpha and your confidence level will add up to 1. If we want to be 95% confident that our data is representing the population, then alpha will have a 0.05 on the other side. 0.95, 0.05. Hypothesis tests and confidence intervals are terms that go hand in hand. So I've got my alpha is equal to 0.05. That's always the case. Sometimes you are asked to use a different alpha. So you can get scenarios in specific fields. Social sciences likes to use 10% level of significance. 5% is the acceptable standard across all fields. Some scientific fields like to use 1% and be even more specific. They want to be 99% confident. So they'll have a significance level of 1%. But normally it's not given. And in cases where that significance level is not given, the acceptable one to use is a 5% level of significance, which translates to 0.05. Now, your p-value that you're going to compare to this alpha, remember you need to check if your p-value is less than alpha to reject. So you're going to take your p-value and it's either the one tail or the two tail. The difference between a one-tailed and two-tailed test is pretty simple. If you think about the format of your alternative hypothesis, because I am strictly looking at the reading time being less than 3 hours, this is a one-tailed test. If I was specifically looking at the reading time being greater than 3 hours, this would also be a one-tailed test. If I was looking at the reading time being different from, so I don't have the sign handy here, but not equal to. Let me see if I can insert it. No, I can't do that here. Hang on, I had it somewhere else. Let me just check quickly if I can find it. No, okay, don't worry about it. But you know what a not equal to sign looks like? It's an equal to sign with a line going through it. Here, I'm just going to write it out. If I was looking at a not equal to 3, this means I can be than 3 or I can be less than 3. And because I can be either greater or less, it becomes a two-tailed test. If I can only strictly be one side, strictly greater or strictly less, then that's a one-tailed test. So our test, our original test of checking if we were under 3 hours, if we're reading less than 3 hours per day, that is a one-tailed test. So this is the p-value that we're interested in. So I'm going to highlight that so that it's clear what the answer we want to look at is. Again, ALUX explains critical values and T-stat values. You can go into that in your self-work. And if this had been a not equal to sign, I would have been highlighting this two-tailed version. But it's not. It's a one-tailed test, so this is the answer that I want. So I can then conclude since my p-value, which is 0.0086, since that number is less than alpha, so I've got an alpha of 0.05, and conveniently my p-value is actually smaller than that number. Because I have passed that test, because my p is less than my a, I can reject h naught, which is exactly what I want. I want to reject h naught and conclude that there is sufficient evidence to say the alternative hypothesis. There's sufficient evidence to prove my claim. There's sufficient evidence to say that students spend less than 3 hours on average doing additional reading. And that is my conclusion. It's a little bit long-winded, but there are specific parts to it that are important to keep in mind. I'm going to go through it step by step and highlight as I go. Let me just format it so you can see it. So I'm going to merge those cells, and then I want to wrap the text. Wrap. Okay. So the specific parts that I want you to remember, I'm going to put them in different colors. Since my p-value is less than alpha, this is an important part. You have to say if your p-value is less than alpha. You also have to say whether you are rejecting or failing to reject H naught based on that. So if I had found that my p-value is not less than alpha, okay, if my p-value had turned out to be, I don't know, 0.12, that would be bigger than alpha, so I'd actually be failing to reject. So it's important to say what your decision is based on whether you have succeeded to be below alpha or not. And then it's important to conclude in terms of your claim. So we want to conclude in terms of our claim, which is that students spend less than 3 hours doing additional reading. I have to see that statement. I have to see that at the end of the day, this is the thing that we were trying to prove. We were trying to see if we have evidence to say this or not. And you'll note that I didn't just say, oh, we can reject H naught, which means that our claim is true, because it's not. We can never say in stats or in anything scientific, you can never be 100% certain that something is true, right? So all we can say is based on our level of significance, based on our alpha, all we can say is that our sample gives us sufficient evidence to say that this claim is happening. Remember that how you sample gives you specific results. Somebody in Singapore could run this test on their students and get a different result. Okay, and all they can say is they have sufficient evidence to say that their result is true, or they don't have to say that their result is true. This is so that if anybody, the reason we say this, I just have sufficient evidence, I have enough evidence from this sample to prove this claim. The reason we say this is so that if somebody else does a test that disproves your claim, you're not caught in a backfire where you had said something was true. You can then come back and say, hey, I only sampled on this group of people in these scenarios. And you also mention, remember, we talked about how you always mention where your sample could be falling short. So this sufficient evidence part is very, very key. So I'm also going to highlight it in green. Okay, and that's your conclusion for this hypothesis test. I hope that has been a useful exercise. Remember as well that when you do these tests, the structure is important. It's important to see what your hypothesis statement is, what the data you're working with is. In your case, because you have a full data set from your Google form that you collected, only bring across the information you need. Sometimes you do that in a pivot table. Sometimes you just copy the column because you are using raw data. It will depend on the question that you're trying to solve, what you need to bring into here in terms of the data that you need to work on. Remember I mentioned earlier that we're using a t-test 2 sample because we don't have a 1 sample, and so our second sample was a dummy variable. We're assuming unequal variances because we've got a variance for this, and the variance for this will obviously be 0. Okay, all of these numbers are the same, so there is no variation to them. So they don't have the same variance. My sample 1 and sample 2 do not have equal variances, which is why I assumed unequal variances. When you have 2 real samples, when you actually have a second sample, maybe you have men and women that you're comparing, if that's always check. So what we did at the bottom here, always check if your stations are almost the same. If they're almost the same, you can assume equal variance. If not, please assume equal variances. And then lastly, just a very quick summary on how to pick what test to choose. I'm going to do this. This is the quickest summary ever. Please bear in mind that your self-work goes into a lot more depth on this. So please read it all and understand it. There's discussions about the sample size. There's discussions about whether you know the standard deviation, and whether you're looking at means or you're looking at proportions. Those are the things that you need to consider when you're choosing what kind of test. Do you run a t-test or do you run a z-test? Okay. We already know if we have a paired sample, then we're running a paired t-test. So that's an easy one. I'll start off with proportions. If you're testing proportions, it is always a z-test. Remember, a proportion comes in the form of a percentage, so that makes it a representative of the population. Because proportions essentially depict what's happening in the population, we use a z-test. It means that's where the question arises. If you're doing averages, you have to think about whether you're doing a z or a t. I'm going to put this one in bold because it's the one you need to remember. So with your means, you will use a z-test. Actually, let's start with a t. You will use a t-test or you will use a z-test. You will only use a z-test if sigma is known. And remember, in the discussion on central limit theorem, we said that sigma is the standard deviation. You either represent your standard deviation with sigma or with S, depending on whether it's coming from the population or the sample. We almost never have population stats, okay? So when you write your hypothesis statement, you use a mu, but when you're doing your calculations, because your calculations are based on the sample, you use an X bar or an S. The reason we use these in the hypothesis statement is because the hypothesis statement is about the population. We're trying to use the sample data to say whether something is happening in our population or not. Okay? To say whether the sample is validating something in our. So if you know sigma, okay, if you've been given that population standard deviation, which is very, very, very rare. It's rare that all the population data and can give you any population. That's a very hard thing to collect population data. But it depends on what the population is, right? So if our population that we're interested in is ALU, then we can have that data. But if our population is all students, there's no way to have all data on all students in the world. Okay? So it's rare that you know sigma, but if you do know sigma, then you can use a Z test. Most often, you will use a T test. So this is what you will use because usually you don't know sigma. Now, be careful. Do not confuse sigma and S. So if you look at this example, just because I can find the standard deviation of this sample, it doesn't mean I know sigma. I know S, I know the standard deviation of the sample, but I don't know the standard deviation of the population. I only know the standard deviation of the populations I can see. So this doesn't mean I know the population, which is why I used a t-test. Okay? I didn't have the standard deviation from the population. I didn't have sigma. I only had S. You always have S. Okay? It's easy to have S. You just do a calculation. What you won't have is sigma. You won't have the population standard deviation. Okay, so this is the basic rule. I'll just highlight this here in, I don't know, let's make it red. Okay, this is the rule that tells you when to use a Z or a T. Like I said, it's a summary, so go through ALU, XK, and once you've gone through that and understood it, then you can just come and see if the summary works for you. It works for me. So with your hypothesis statements, always think about, am I doing proportions? If you're doing proportions, then it's a Z test. If you're doing means, then it's a T test or a Z test. Z test if you know the population standard deviation. Otherwise, you're doing a T. Chances are in this data, because we don't have population information, if you're testing anything with a mean, you're probably going to use a T. You'll see as well that XLMiner for proportions, XLMiner only has a Z test for 2 sample means. Again, if you're doing proportion, this is the one you will use. It will still work for proportions, and I think this is explained in ALUX. It's pretty similar. You just use your select your data ranges the way we did. And if you have a hypothesized value, it goes in there. If you are doing a one sample, then you have to create a dummy variable. And then these are your variances if you know them. If you don't, then you don't. Alpha, like I said, is always set at 0. You only change this if you have been instructed to do so. So if you are now doing your degree programs and you happen to need to do a hypothesis test, check with your supervisor or your facilitator what significance level they want you to use. If they say just use the normal one, they mean 5%. Okay. I hope that's been helpful. I will only share this on Monday after office hours. For now, please watch it and try and do some of these examples on your own. Try and do them with the real data that you've actually got for your assignments. And all the best, everyone.